Bismillahirrahmanirrahim. ELE424 Analog Electronics 1. We are now ready to look at more diode applications, clipper and clamper circuits. Okay. This is the video 3 from the video pack 2. We have completed our previous video, which was rectifiers. Okay, so we will cover two circuits for this video, which is the clipper circuits and the clamper circuits. And when I cover both, I'll start off with the introduction, which will give you some appreciation of what the circuit is all about and some practical applications that the circuits would be useful for. And then we look at examples and circuit analysis involving clipper and clamper circuits. Clippers. Okay, what is a clipper circuit? So clippers can be used to shape a waveform. Just as our previous lecture, which was on rectifiers, we are now handling circuits that will receive an input signal in the form of a time-varying waveform. Okay, so the input signal can either be a sinusoidal wave or a square wave or anything that varies with time. So clipper circuits, also called limiter circuits, okay, they are also known as limiter circuits, are used to eliminate portions of a signal that are above or below a specified level. So it shapes the waveform by eliminating some portion of the signal. So you can imagine in your mind that the sinusoidal wave will now become clipped. It will become flat in certain areas. Okay. Clippers are networks that employ diodes to clip away portion of an input signal without distorting the remaining part of the applied waveform. Okay. So it uses diodes. That's why it's under diode applications, and it will clip certain parts, but it will maintain other parts of the waveform. So example of a clipper, we've actually seen a clipper before, and that is a half-wave rectifier. So the half-wave rectifier is the simplest form of diode clippers because it eliminates one of the cycle of an AC signal. So it either eliminates the positive cycle or the negative cycle of the input voltage. Okay, so this is an example. This was the half-wave rectifier, the simplest rectifier that you saw in the previous lecture. So this is also a clipper. If you input a signal waveform of a square wave, you can clip, say, in the negative cycle, or you can also clip the positive cycle and maintain the negative cycle. If it's a triangular wave, you can eliminate the negative cycle as well as the sinusoidal that we handled last lecture. So what practical applications would use clippers? Okay, just as in our previous lecture for the rectifier, I cited the application of power supply, DC power supply. I figured that every time I state a circuit application that we cover in ELE424, that I should also include some practical applications so that you understand that the circuits that we're talking about, they're real. They are in applications, and they are used perhaps not in the simplest form that we cover in our lectures, but they are useful circuits. Okay, so diode clipping circuits can be used in voltage limiting applications. Okay, voltage limiting means you want to limit the voltage values. For example, it can be used to eliminate portion of signals above or below a certain values as part of a protection circuit. Okay, when high voltage spikes occur by not allowing high voltage values to be applied to a load. So for example, let's say this one here. Okay, I've added a whole list of examples here. So for example, I can have for circuit part C an input signal, and I can protect the load at the output here. If I put the load at the output here, whatever voltage that is applied here will not be more than 0.7 and will not be less than negative 0.7. Okay, perhaps that's the specification of the load that you want to use, that it should be just between negative 0.7 and plus 0.7. So this would be the circuit to protect the voltage that covers this load. So anything more than that, if the input voltage tries to apply more than 0.7, it would have been flattened out. Okay, it would have been remained at 0.7 or negative 0.7. Okay, so for flexible clippers, Okay, for real clippers, sometimes an op-amp may be included with the diodes, but that is not covered in this course. I'm just saying that the circuits here will not be just resistor and diodes. These are the simplest form that we cover for the sake of this course. So what can be clipped? I'm still at the introduction here, just so that you have a rough understanding of the applications of this clip circuits. So what can be clipped? So if you put in an sinusoidal wave, okay, you put it in a clipper circuit, okay. Before we go on, although the input voltage to diode clipping circuits can have any waveform shape in a real world, so you're not going to have just sinusoidal wave, right? You just can have any waveform shape. We will assume here in this course that the input voltage is commonly sinusoidal, square or triangular wave to represent an input signal, to keep it simple. Okay, so we can have, say, we can clip the negative cycle, or we can clip the positive cycle. We can clip more than the negative cycle up to a certain level of the positive cycle, or we can clip just a certain part of the negative cycle that we maintain, or we can also increase the voltages by shifting it by applying some applied bias. Okay, you'll have a look at this later. Or we can clip and maintain it at a certain voltage. Instead of clipping and going all down to 0 volts, you may want to fix it up to a certain voltage here. So here it may involve added bias. Or you can clip the negative cycle but only a portion of the negative cycle, or just a portion of the positive cycle, or you can clip just a portion of the positive cycle and a portion of the negative cycle. So how do we know which circuit does what? You'll have to do an analysis of the circuit, and different kind of circuits. You can have a single diode or a combination of parallel diodes. You can add resistors and voltage bias to the circuits to get the different kind of waveforms that you want here out of the input signal. So the different diode orientations, connections and combinations will give different effect to the output waveform. Still at the introduction, so these are the circuits that I said. You can have different orientations, you can turn it the other way around, you can add added bias, you can have it parallel, or you can have it in series with the V out, with the load that has the expression voltage across V out, or you can have it in parallel, or you can have two diodes in combination. Okay, so these are I'm just putting it here so that you can imagine what are the circuits that you might be facing when you do the tutorials. Okay, basic concept. Now we're ready to look at clipper's basic concept. This diode in series, in a series clipper, what it does is that it clips any voltage that does not forward bias it. So that's the power of this diode, because it allows current in one direction, and it allows current when it's forward biased but not reverse biased. That's how it does its clipping action. Okay, so if I were to do my analysis, if I were to look at, now let's just have a look at the sinusoidal. I have a positive cycle of the input and a negative cycle of the input. Okay, and I know that when it is positive, if you look at the laser pointer that I have on screen, okay, if it is positive, it would be forward biasing the diode because it is in the direction of positive current flow. But if it is a negative cycle for Vn, it would then be attempting to flow when it's applying reverse bias. So in the negative cycle, the diode would be non-conducting. So if I consider when the diode is conducting, when it's on in the positive cycle, okay, and if I do a diode on, this would become a short circuit, which means that Vd is equals to 0 because this is an ideal diode. And if I do a KVL, okay, I'd get minus Vin plus 0 plus V out is equals to 0, so V out is equals to Vin. So when it is on, which is the positive cycle, V out imitates Vin. V out is equals to Vin, and when Vin is maximum, V out is also maximum. But when it is negative, okay, when it is negative cycle, the input would be attempting to flow in the opposite direction of positive current flow, and this diode would be reverse bias, so this diode would be non-conducting. And if I do an equivalent circuit for the ideal diode, this would be an open circuit, which means ID here would be 0, which means the current through this resistor would also be 0. So if I do Ohm's law across this resistor, follow my laser pointer, it would become V out is equals to 0 times R, which is equals to 0 volts. So in the negative cycle of the input, the corresponding V out is just going to be 0 volt. And when this sinusoidal repeats itself, if you follow my laser pointer, this output would also go from positive to 0, and then it goes to positive 0, positive 0. Okay? So effect of adding bias. Now what happens if you add bias to our simple diode resistor circuit? Adding a DC source in series with the clipping ideal diode changes the effective forward bias of the diode. It's like, you know, it's like having a silicon diode forward voltage, but this is an added voltage, an added bias. So what's going to happen here? What's going to happen is that you're still going to have the same sinusoidal. It will still be clipped, but it's going to be clipped, okay, at a value that is higher than 0 volts. Okay, so it will maintain the positive cycle above this added bias voltage added. Yes. Okay, so and it will follow V out will follow V in, not starting at 0 volts, because volts, this added bias V is not at 0 volts. V is slightly after 0 volts. So V out will also start to imitate V in slightly after 0 volts, and it would stop imitating V in before T over 2, which is half of the cycle. So it changes state before and after, because we have added a DC source in series with the clipping ideal diode. So let's have a look at an example. Let's do some values here, or some calculation. Alright, so I have a we have the diode just as we had earlier. Okay, we are adding a voltage source V, okay, which I'm going to call VA, because, you know, just V is just can be some voltage. So I'm going to give it a name, VA, and I know that it would be forward bias when the input signal is in the positive cycle, because it would be in the positive direction of current flow. But if it is in the negative cycle, it will be attempting it to be reverse bias. So during the negative cycle, it would turn off, but in the positive cycle, it would turn on. So when it's on, diode is a short circuit. VD is equals to 0, and if I do a KVL, I get negative V in plus VA plus V out is equals to 0. So now my V out is not just V in, but V in minus VA. And when my V in is a maximum of VM, which is this one, VM, I can expect that my V out maximum is going to be VM minus VA. So when it is off, it's still the same story, because when it's off, diode is an open circuit. ID is equals to 0, and if I do Ohm's law here, V out is going to be equals to IR, 0 times R, which is equals to 0 volts. And if I plot the V out versus time aligned with V in versus time, this is what I get. Okay, so VM maximum of the output voltage is now no longer VM, but VA, VM minus VA. Okay, and it turns on before right after 0 volts, and it turns off again right before T over 2. Okay, and how do I know when, at what value does it turn on? Okay, if it's a straightforward case, maybe we can figure out that it turns on, this conducting stage starts at changes state at added bias volt, but sometimes it's not that straightforward. So it's always good to consider KVL to do transition voltage and to find the transition voltage, and transition voltage is when diode turns on. So when we try to find what the transition voltage is, we consider at the point where the diode starts to turn on, but there is no current flow through it yet. So this is the point that we use. Let VD equals to 0 volts and ID is equals to 0 amps. So this is new for our consideration. I'm just going to highlight it. Okay. So this one here, It's important. When you want to find the transition voltage, let VD is equals to 0 volts and ID is equals to 0 amps. So when I draw the circuit, this diode here becomes a 0 volts, just like a short circuit, but ID is going to be 0 amp. And the reason why we're doing this is because we want to find an expression for V in that tells us when the diode changes state from conducting to non-conducting. So when I do this, when I let this value in and I do a KVL, I get negative V in plus VA plus 0 volts, which is from the diode, plus 0 volts, which is from the resistor, equals to 0. I get this value V in is equals to VA. So I know that diode changes from on to off at V in equals to VA. This one here, I should add. Okay, Vn equals to Va. Okay, so general steps to consider for circuit analysis in clipper circuits is that first you have to decide when the diode turns on and off and find V out with respect to V in for each case of when it turns on and it turns off. So how do we decide? You have to check the direction of voltage cycle, which is the input AC voltage, and the effect on the current through the diode. Also check direction and value of the added voltage source and its effect on the turning on diode. Are the values going to be not possible for the diode to turn on because it's not enough to supply the forward voltage or not? And then for each part, you determine V out with respect to V in when the diode turns on, and then determine V out with respect to V in when the diode turns off. I think there is a typo here. Okay. First you find, if I can find my pen. Okay. First you find it when it's on, and then you find it when it's off. Okay. Okay. Then next, once you know what the expressions for V out is with respect to V in for each of the state when the diode is on and diode is off, then you determine the transition voltage that turns the diode on and off. And to determine the transistor voltage, you have to let VD to be 0 volts and ID to be 0 amps. And this is needed to determine when diode V on is reached. And then you draw the output waveform with respect to input based on what you have found from the KVL above and the transition voltage, and you have to establish the clipping level and peak output voltage based on the values that you have found. Okay, so now we are ready to do examples. Alright, example series clipper with a 5 volt bias sinusoidal input V in. Okay, and so I have a sinusoidal input V in, which peaks at 20 volts. Okay, and I have an added bias here, which is 5 volts. Okay, so it doesn't say anything about the diode, so we assume that the diode is ideal. So diode is on, looking at this at the positive cycle, because in the positive cycle, the current flow would be in the direction of positive current flow. So when the diode is on, the diode is a short circuit. VD is equals to 0 volts, and if I do, okay, and take note that I have added the added bias here, which is 5 volts, the negative terminal and the positive terminal as indicated in the question given. So I can do a KVL around this loop. I get negative V in minus 5 plus 0 plus V out is equals to 0. So I get V out is equals to V in plus 5. So when V in is a maximum at 20 volts, my V out is a maximum at 20 plus 5, which is 25 volts because of this added bias here. Okay. Now when it is negative cycle, okay, when it is negative cycle, diode is an open circuit, so ID is equals to 0 when I do an Ohm's law at this resistor, because ID is equals to 0, and that's the current that flows in this circuit here. So V out is equals to 0 times R, from V is equals to IR, so V out is equals to 0 volts. Now next is to find the transition voltage when the diode turns on, and as instructed, the transition voltage we can find if we let VD equals to 0 volts and ID equals to 0 amps. And from there, VD is equals to 0 volts, ID equals to 0 amps. From there, we do a KVL around this loop. I get negative Vin minus 5 plus 0 is equals to 0 volts. So Vin, from here, I get Vin to be equals to negative 5. This means that the diode switches from conducting to non-conducting, on to off at Vin equals to negative 5 volts here. Okay, negative 5 volts here. And if you look at negative 5 volts, that means it happens, okay, in the negative cycle after the T/2 period, okay, time. After the T/2 time, and it would turn off. It would turn off after T/2, and it would turn on again before the cycle ends at T. Okay, so if we draw it, this is what's going to happen. Okay, we have V out imitating V in with an additional 5 volts before 0 volts, not after 0 volts, but before 0 volts. And we have it still imitating after T/2, just after T/2. Now, right after that, when V in reaches negative 5 volts, at this point, okay, at this point, the diode becomes non-conducting. And when it is non-conducting, V out is equals to 0 volts. When it is conducting, V out is equals to V in plus 5, which is why it reaches up to 25. But when V in is equals to negative 5, which is the transition voltage, V out is now 0 volts. And that's how we get this curve. So again, if I have a repeating cycle of sinusoidal going up and down as my laser pointer here, okay, I'm going to have 0 volts when diode is not conducting. And then it becomes positive before 0 time, and then it goes back down to 0 right after T/2 is reached, and before T is reached again, before, not at time T, but before time T, it will start to imitate V in with an additional 5 volts again. Okay, that is the effect of having a 5 volt bias. One is that the maximum value is shifted up, and the time that it changes on and off is also shifting. Instead of 0 to T, it would be before 0 and after T/2. Okay, now what happens if the input is a square wave input and not a sinusoidal input? The analysis is the same. It's actually the same. I think I've just recopied the same analysis. But as you interpret what is given here, okay, we know that when it is positive cycle, it will turn on. So, and it's always maximum because it's not sinusoidal, it's a square wave. Okay, so all the way it is always 20 volts for V in. So all the way I can imagine that my V out will also always be 25 volts. Okay, and then when it turns off, okay, in the negative cycle, which is this one here, my V out is going to be 0 volts. So when it's on, when the diode is on, it's going to be 25. When it's off, it's going to be 0 volt. And the transition voltage here says that it will occur at negative 5, but you can't actually see it at the period here because it goes to negative 5 at T/2. So we're going to have the same T/2 occurrence of between on and off, but now we have, instead of 20 to negative 10, we have it going from 25 to 0 volt. We have clipped the negative cycle and we have shifted the value of maximum value with the edit bias. So now what happens if we have the diode, instead of the diode negative terminal connected in series with the point where V out terminal is, what happens if we have the diode in parallel to the points that we want to calculate V out? So the diode in a parallel circuit, clipper circuit, is just the same as it was in our previous example, is that it clips any voltage that forward biases it. Okay, so we have whether it is a sinusoidal, square wave, or a triangular wave, it does the same, but it would clip different parts of the circuit because the orientation has now changed. The connection has also now changed. Okay, so now let's consider this circuit. It will be forward biased in the positive cycle, and then it would be reverse biased. I should have the laser pointer on. It will be reverse biased if it is in the negative cycle. So now when it is on, okay, the diode becomes a short circuit. This diode here becomes a short circuit, and VD is equals to 0 volts, and V out is going to be the voltage across the short circuit. So V out is going to be equals to 0 volts. And when it is off, okay, when this is off, it becomes an open circuit, and if it becomes an open circuit, ID is equals to 0. Now for me to find V out is now not 0 volts anymore, but V out is now the voltage that depends on this network. So if I do a KVL around this loop, okay, I'm going to get negative V in plus 0, because ID is equals to 0, so Ohm's law across this resistance is going to be 0 volts, plus V out is equals to 0, so V out is equals to V in, and when V in is a negative peak, because you're considering the negative cycle, when it is at the negative peak of negative Vm, V out is going to also be equals to negative Vm. So the effect here is that when the diode is on, it clips. Okay, it clips at this point, opposite to the one that is in series. You don't actually have to remember it. You can always consider in your head, in your mind, you can consider what happens when it's short circuit and the calculation of Ohm's law and KVL. So here you omit the positive cycle and you keep the negative cycle when it is off. Okay, another example of parallel clipper added bias with triangular wave input voltage. What if you have a triangular wave? Okay, so if you have a triangular wave like here, okay, now we know that again we know that it will turn on and off depending on the orientation of the diode, whether it forward biases it. So if I look at this orientation, when it is positive cycle, it would be opposing the positive direction current flow, so it will be reverse bias. So when it is in forward bias, when it is in positive cycle, the diode will be off, but when it is in the negative cycle, okay, the diode will be conducting because it is in the direction of positive current flow. So diode is on during negative cycle, so we consider the negative cycle first, and when it is on, VD is equals to 0 volts because it's an ideal diode. So we've redrawn the circuit here. Okay, I have maintained V in positive and negative here, whether it's positive cycle or negative cycle, because it's still the same V in, and we can consider that accordingly when we put in our values. Okay, so the voltage drop across here is going to be 0 volts, and V out is now the voltage across this path here, this branch here, okay, which includes the short circuit and the 4 volts added bias. So V out is actually just 4 volts. So when the diode is on, V out is 4 volts, and when the diode is on, it occurs in the negative cycle. But when the diode is off, which is for the positive cycle, okay, when it is off, it becomes an open circuit. ID is equals to 0. Then I have negative V in, I have R, and I have V out. And the voltage for V out, I can figure out if I do a KVL around this loop. Okay, so if I do a KVL here, I'm going to get negative V in plus 0 plus V out is going to be equals to 0. So V out is going to be equals to V in. So now in this case, the diode that is off will cause V out to be equals to V in. And if this is the expression, if V in is maximum at 16 volts, V out is also maximum at 16 volts. Now next question is, when is it going to do the transition? Is it going to be positive 4? Is it going to be negative 4? So for us to be sure, we will assume VD is equals to 0 volts and ID equals to 0 amps. We will let these values to be applied because we want to find the transition voltage at the point that it switches. So KVL around this loop will give me negative V in plus IR, which is 0 volts, because we have said that we are forcing this ID equals to 0 amp value here, plus 0 volts because we are forcing VD to be equals to 0 volts. Okay, and plus 4 is going to be equals to 0, so the transition voltage occurs at Vin equals to 4 volts. So which means Vin is equals to 4 volts. If it's a complete cycle from 0 to t like what is given in this graph here, if it is 4 volts, it will turn on, okay, V out will turn on and off, it will switch states at a value right after 0 time and right before t over 2, okay, and in between, when it is off, V out will imitate V in, but when it is on, the value will be 4 volts, not 0 volts. Now this graph does not go down right through the axis, but it stops at 4 volts. Okay, so that is the effect of having an added bias of 4 volts and having it in parallel. Another example, clipper with triangular wave input, the same one in the previous example, but now using silicon diode. Now when we have a silicon diode, okay, we have to consider again this diode, which is the positive and negative terminal is orientation. So I have here 0.7 volts drawn in this connection because this is the connection of the diode. Okay, so now I have here 4 volts, okay, in series with a 0.7 volts voltage source. So if I find V out, it's going to be the total voltage drop across this path. So it's going to be -4 plus 0.7 plus V out is equal to 0, which will give me 3.3 volts. And when it turns off, V out is still V out is equals to V in. Okay, and when V in is equals to 16 volts, V out is also equals to 16 volts. And for the transition voltage, now the maximum value is not affected, okay, because of this considering of the 0.7 forward voltage, which is still 16 volts, but the transition voltage will change because it will turn on once you consider the 0.7 volts drop as well. So let Vd equals to 0.7. Now at that point of turning on, it's not 0 volts anymore, okay, because this forward voltage is now 0.7, and the ID is equals to 0 amp, because this is what we are forcing. If you don't understand at this point, please go back a few slides to see what it means to get the transition voltage, because that's where the concept is. Okay, and then if we do a KVL around here, we have negative V in plus 0 plus it's going to be negative minus 0.7. Sorry, so it will be, okay, let me start all over again. It will be negative V in plus 0 minus 0.7 plus 4 is equal to 0. So the transition voltage occurs at 3.3 volts. So this is how the output voltage will look like. It's just the same as the one before, but the transition voltage now occurs at 3.3 volts. Okay, and it also maintains the value 3.3 volts when the diode is on. We are now ready to go to the next topic, clampers, which will be in the next video. Thank you.